This week, we are going to be discussing mixtures. So please listen and read along as I read pages 46 through 50 in your FOSS ebook. Page 46, Mixtures. If you visit a lake or beach, you might see something like this at the water's edge. What's there? A mixture. A mixture is two or more materials together. This beach is a mixture of sand and gravel. A handful of this mixture contains bits of rocks of many different sizes. If you wanted to separate the gravel from the sand, how could you do that? You could pick out all the pieces of gravel one by one, but there's a faster way. You could use a screen. A screen has holes small enough for sand to fall through. Pieces of gravel, however, are too large to pass through. They stay on top of the screen. Screens are useful tools for separating mixtures based on the property of size. If you look down here, the caption for the picture says, "A screen can separate sand and gravel." Imagine opening a kitchen drawer to get a rubber band. Oops, the rubber band spilled. So did a box of toothpicks and a box of paper clips. The drawer contains an accidental mixture of rubber bands, toothpicks, and paper clips. How can you separate the mixture? You could use the property of shape. You could pick out each piece one at a time. It might take 10 minutes to separate the mixture. Paper clips are made of steel. Steel has a useful property. Steel sticks to magnets. If you have a magnet, you can separate the steel paper clips from the mixture in a few seconds. Magnetism is a property that can help separate mixtures. What about the toothpicks and rubber bands? Wood floats in water. Rubber sinks in water. The properties of floating and sinking can be used to separate the wood toothpicks and rubber bands in seconds. Drop the mixture into a cup of water. Then scoop up the toothpicks from the surface of the water. Pour the water and rubber bands through a screen. The water will pass through the screen, but the rubber bands won't. The job is done. If you look down here at the bottom, the captions say a mixture of rubber bands or a mixture of paper clips, rubber bands, and toothpicks. So this is what it would look like in the drawer if it got all mixed up. So first, they separate the steel paper clips with a magnet, and then they separate the toothpicks and rubber bands in water. See how the toothpicks float to the top and the rubber bands all sink to the bottom? It kind of looks like a cup of noodles. Solids and liquids. Mixtures of solids and liquids are interesting. Several things can happen. When sand and water are mixed, the sand sinks to the bottom of the container. If you stir the mixture, things move around, but that's about it. When you mix chalk and water, like down here, the chalk makes the mixture cloudy white, and after a while, the chalk settles to the bottom. When you mix salt and water, the salt disappears and the mixture is transparent and colorless. Sand, chalk, and salt all make mixtures with water. After stirring, you can still see the sand and chalk, but the salt has disappeared. Salt is different in some way. A mixture of salt and water forms a solution. A solution is a special kind of mixture. When solid salt and liquid are mixed together, the solid disappears into the liquid. The solution is transparent. When the solid salt disappears into the water, it is not gone. It has simply dissolved. When a solid dissolves, it breaks into pieces so tiny that they are invisible. When salt dissolves in water, it makes a saltwater solution. Conservation of matter. There's one more thing to think about when you make a mixture. All matter has mass. Anything that has mass is matter. If you have 50 milliliters of water in a cup and add 30 grams of sand to the cup of water, what will the mass of the mixture be? The mass of the 50 milliliters of water is 50 grams. So the mass of the mixture will be 50 grams of water plus 30 grams of sand equals 80 grams of total mixture. That seems pretty easy to understand. But the mixture of salt and water is a little trickier to think about. When you mix 30 grams of salt with 50 grams of water, what do you think the mass of the mixture will be? The salt disappears into the water, so what happens to its mass? Did you conduct this investigation? The mass of the clear solution is 80 grams. That is the sum of the mass of the water and the mass of the salt. The mass of a substance like salt does not change when it dissolves. Even if you can't see it, the salt is still there and its mass has not changed. In fact, mass never goes away. Mass is conserved. Therefore, the matter is conserved. This means matter can change shape, state, or location, but it can never be lost or destroyed. So that's what our top picture and caption says. Matter is never destroyed, but it can change. For example, wood, the matter in this picture, changes to ash when it's burned. Sometimes it's hard to understand how matter is conserved. For instance, when you have a campfire, a large mass of wood burns, and all that's left at the end of the evening is a small pile of ash. If matter is conserved, where did the mass of the wood go? Well, the fire produced several things. It produced smoke, light, and heat. Light and heat are energy. Energy is not matter. Smoke is a gas and tiny particles of soot. Gas and soot are matter. That's where the wood went. The fire changed most of the mass of the wood into gas and tiny particles. The particles drifted off into the air. Gases and tiny particles have mass. If you capture all the smoke and dust coming up from the fire and gather up all the ashes, what would you find? You would find that the mass of the gas and ash would add up to the mass of the wood you put in the fire earlier. Conservation of matter is just one of the great truths of nature. Matter can never be destroyed, but it can be changed. As you continue your investigation of mixtures, you might find an instance where your observations suggest that matter is not conserved. But matter is always conserved. You will have to do some deep thinking to explain why your evidence suggests that matter is conserved.